Welcome. In this lecture, we are going to start our discussion on sequence and series of functions. So, in the basic course of real analysis, we might have studied about sequence and series of real numbers and sequence in some general metric space setup, right? Okay, and here, as the title suggests, it is a sequence and series of functions. So, the sequence that we are going to consider here is no longer a mapping from, basically sequence is a mapping from where sequence is a mapping from the set of natural numbers to any set x, right? Okay, here since it is a sequence of functions, it is no longer a mapping from n to any metric space x. It would be n cross some set. Okay, n cross some set to some other set. Okay, it may be x or some other metric space. Okay, so let me specify it in general case. So it will be of this form. So here the entries we will write it in this form, where your n is a member of a set of natural numbers and x is a member in the set x, and this fn of x would be a member in y. So we are going to discuss sequences of this form, and we are going to restrict ourselves to the sequences which are complex valued functions. So basically this fn of x would be in C or in R. So only these kind of functions, sequences we are going to discuss in this in the upcoming few lectures. Okay, we will begin the main discussion. Okay, first let me present a definition. Suppose fn is a sequence of functions defined on a set E, and suppose that the sequence of numbers fn of x converges for every x in E. Then we can define a function small f by means of f of x equals limit n approaches to infinity fn of x, where this x in E. So now we are saying that it is a sequence of functions which is defined on a set E. Here, what is that set E? It is completely unknown. Okay, it is some set from any metric space. That is not a bother here. And we say that the sequence of numbers fn of x converges for every. As I said before, we are going to restrict our discussion. We are going to restrict ourselves to the complex value functions at the maximum, or it may be real valued as well. Okay, now we define a function f by means of this. So for every point x in E, we just substitute a particular point of E into this function, and we will have a sequence, and that if that sequence converges to some point, that point we pick, and this is continuously done for all values of x, and finally whatever we get, that we put it, we represent it as some function f of x. Okay, so in this circumstance we say fn converges on E, okay, and this f is the limit of convergence. But now we have a question that whether this f is a limit of the sequence fn or limit function. In the discussion of sequences and series, it is just the limit of a sequence. But here it is a limit or the limit function. It is a question mark. Okay. So here we have established some convergence. If one such function, if we are able to define for all the values of x in E, then we call that f as the limit function. So in order to clearly specify this, what we are going to say is that the sequence fn converges to f pointwise on E. So by this, what we are trying to say is that we fix a particular value of x, and once that value is fixed, we have a sequence on E. It is no more a sequence of functions. Once the value of x is fixed, it is just a sequence of sequence, and that is converging to some point. If a sequence converges for every point x, then we say the sequence fn, sequence of functions fn of x converges to f pointwise, or we can fn of x converges to f pointwise on E. We can say this way as well. Okay, and similarly, if summation fn of x converges for every x in E, and if we define f of x to be summation n runs from 1 to infinity fn of x, where x is in E, then the function f is called the sum of the series summation fn. So the series convergence is associated with the convergence of the sequence of partial sums. The same ideology can be used here to verify this discussion, okay, or to understand this discussion. Now, okay, so now that we have seen what do we mean by a sequence of functions and a series of functions, what is their convergence, so, and this is done. Now supposing we have a sequence of functions, okay, that sequence consists of all continuous functions. Does it imply the limit function is also continuous? If the sequence is of differentiable functions, whether the limit function is differentiable. If the sequence is integrable, whether the limit function is integrable. All these questions are still unknown. Okay, they are to be answered. Okay, now let me consider an example. So for m equals 1, 2, 3, etc. and n equals 1, 2, 3, etc. Let us define some Smn, a double sequence, to be m upon m plus n. Okay. Now my question is whether it can be treated as a sequence of function. Yes, very well, it can be treated as a sequence of function which is defined from n cross n to r. So one n, that makes it to be a sequence, another n, that is some random set, okay, and it is a real valued function, right? Now, so this way it can be treated. Now let us see that for every fixed n, Here we are fixing n. Okay, then the varying quantity is m. When we take limit m approaches infinity to this smn, so m is tending to infinity, so we just take this m out. Okay, it would be a limit m approaches to infinity, m can be taken outside, so that would be 1 plus n upon m. M gets cancelled and this limit is 1. Okay, now if you let your n also go to infinity to this, what is happening? It is 1 only. Okay, whereas on the other hand, if you fix m and if you let n go to infinity smn, what is happening? So it is simply m upon m plus n. Nothing can be taken outside, so it is directly 0. Therefore, your limit m approaches infinity, limit n approaches infinity, smn is 0. So here, even though it is a double, like as I said, it can be treated as a double sequence. Okay, one thing is, one set of natural numbers is to denote that it is a sequence. Now first we have treated that as a sequence based on n and found the limit. On the other hand, we just did the reverse. Okay, but here what did we achieve? Limit m approaches infinity, limit n approaches infinity, smn is not same as that of limit n approaches infinity, limit m approaches infinity, smn. Okay, this is so even in the double sequence, this limit is not the same. So something is an issue here, right? Yeah. But as separately, if you focus, okay, we are able to see that it is converging pointwise. If you fix a particular n, okay, once your n is fixed and if you treat it as only as a varying quantity in m, that sequence converges to 1. Okay, on the other hand, we have a sequence that is converging to 0. Okay, so pointwise convergence is that to some extent, but still they are not the same. We are able to get two different pointwise limits, but they are not same. Okay, so now we will proceed further and we will proceed with another example and try and understand what is the phenomena behind all these discussions. Okay, here let us consider fn of x to be x square upon 1 plus x square to the power n. Okay, x is any real and n is this. So basically here your fn of x is a mapping from n cross r to r. And f of x is nothing but summation n runs from 0 to infinity fn of x, that is summation n runs from 0 to infinity x square upon 1 plus x square to the power n. Okay, now let us note that if x equals 0, then what happens? Our fn of x is 0, isn't it? Since the denominator has 1 plus 0 to the power n, so it would be 1 only. In the numerator we have 0, therefore it is 0. Then our f of x is 0. Okay, if x is not equal to 0, then x square upon 1 plus x square to any positive power n is less than 1. Okay, thus our f of x, which is summation n running from 0 to infinity x square upon 1 plus x square to the power n, is a geometric series with what is the first term? When we substitute n equals 0, x square is the first term. X square being first term and 1 upon 1 plus x square being the common ratio. Therefore, using the infinite sum rule, that is first term upon 1 minus common ratio. So it would be x square upon 1 minus 1 upon 1 plus x square. So what do we have here? X square upon 1 plus x square minus 1 multiplied with 1 plus x square. So things gets cancelled and this is what we have. Hence, our f of x is nothing but 0 if x is 0 and it would be 1 plus x square when x is not equal to 0. Okay. Observe our fn of x, that is x square upon 1 plus x square to the power n, is a continuous function for all x in R, but f of x is discontinuous at x equals 0. So we had a series of continuous functions, but the limit of that series is discontinuous. So even though we have the pointwise limit, the property is not preserving. Okay, so we just discussed this for the double sequence case and continuous function case, and we are yet to explore more on this scenario and what would make the property preserves under this limit. All these things we will discuss in the upcoming lectures. Thank you.